Most people think building quantum computers is just about wiring up more qubits. But the real battle is against a silent enemy, decoherence, that wipes quantum memory clean in under 1,000th of a second, no matter how cold or carefully engineered the system. The best machines on Earth must operate at 15 millikelvin, yet even then, quantum information decays so quickly that running even a basic algorithm is a race against vanishing time. Why does nature make remembering so impossible? And what does it take to defy these odds? Inside a quantum computing lab, the numbers tell a story that borders on unbelievable. Superconducting qubits, tiny circuits chilled to 15 millikelvin, colder than the darkness between the stars, hold on to quantum information for just 50 to 300 microseconds. That's less time than it takes for a single nerve signal to travel from your finger to your brain. Even with years of engineering and millions invested, the world record for coherence in these systems barely scrapes past 1 millisecond. IBM's Heron R2 processor, announced in late 2024, managed to stretch that fragile memory out to the millisecond range, thanks to a relentless campaign against material defects and stray energy. Google's Willow chip, also in 2024, achieved a mean coherence time of 68 microseconds, a technical feat, but still a blink compared to the needs of most algorithms. Dr. Jay Gambetta, one of IBM Quantum's leading voices, summed up the challenge bluntly: "We're fighting for every microsecond." At these timescales, a quantum computer can perform only about 1,000 gate operations before its memory evaporates. That's the upper limit, even under the best conditions, when every atom is in its place and every stray photon has been banished. Trapped ion qubits, by comparison, can maintain coherence for seconds or even minutes, while photonic qubits preserve their quantum state as long as they keep moving. But for the superconducting circuits that dominate the race to build practical machines, the clock is always ticking. The result is a system that forgets almost everything before it can finish a thought, a machine designed to remember, yet haunted by amnesia, at the speed of light. Quantum decoherence isn't just a matter of time slipping away, it's the result of specific microscopic events inside every quantum chip. At its core, decoherence describes how a qubit's fragile quantum state becomes tangled with its environment, erasing the superposition that powers quantum computing. This process is captured mathematically by the density matrix, where the key quantum signature, the off-diagonal terms, decays exponentially, following the formula ρ01 of t, approximately ρ01 of 0 times e to the minus t over t2. Here, t2 is the dephasing time, the clock for how long a qubit can maintain its phase coherence before random environmental noise scrambles it. T2 is always less than or equal to twice the energy relaxation time, T1, which measures how quickly a qubit loses energy and falls from its excited state back to the ground state. Both T1 and T2 are under constant assault from the materials that make up the chip itself. Two-level systems, TLS defects, are a prime culprit. These atomic scale traps, scattered throughout the dielectrics and at the interfaces of Josephson junctions, act like tiny sponges, soaking up energy from qubits and shortening T1. They also create fluctuating electric fields that jitter the qubit's phase, eating away at T2. Even when chips are cooled to 15 millikelvin, stray thermal photons, electromagnetic fields, and vibrations keep these defects active. The result is a relentless exponential decay of quantum information, driven not by a single catastrophic event, but by millions of microscopic imperfections working in concert. Each gate operation, each nanosecond, brings the quantum system closer to classical noise, forcing engineers to race against a tide of invisible, atomic-scale saboteurs. Cosmic rays, invisible and relentless, bombard the Earth every second. In 2020, a collaboration between MIT and Pacific Northwest National Laboratory revealed that these high-energy particles create a hidden ceiling for quantum computers. Even in perfectly engineered superconducting chips, cosmic radiation triggers a cascade of effects deep within the hardware. When a cosmic ray or a burst of natural radioactivity from concrete walls strikes a quantum processor, it breaks apart pairs of electrons known as Cooper pairs. The resulting quasi-particles spread across the chip, poisoning qubits and cutting their memory short. This process sets a hard upper limit. In unshielded labs, coherence times for superconducting qubits can never reliably exceed 4 milliseconds. No amount of cooling or material perfection can erase this fundamental barrier. Professor Mikhail Lukin, a leading voice in quantum information science, has described the cosmic ray problem as a direct assault from the universe itself. Shielding strategies have become essential. At Canada's Snow Lab, quantum devices are tested 2 kilometers underground, where rock blocks nearly 1,000,000 times more cosmic radiation than the surface. Heavy lead and concrete enclosures add another layer of defense, but even these solutions come with steep costs and technical challenges. The threat is not theoretical. Every cosmic ray event is a real risk, capable of corrupting data across an entire quantum chip in a single instant. For quantum engineers, the universe is not a silent backdrop. It is an active, unpredictable adversary, setting the rules for how long quantum information can survive. Every operation in a quantum computer is a gamble, with the odds stacked against success. Physical gates, those basic building blocks that flip, rotate, or entangle qubits, fail between 1 in 1,000 and 1 in 100 attempts. That's an error rate between 0.1% and 1%, orders of magnitude worse than the 1 in 100 quadrillion error rate of a classical transistor. Each quantum gate compounds the risk, and quantum algorithms often require thousands or even millions of these operations. Without correction, the probability of a quantum computer producing a meaningful answer collapses almost instantly, leaving only random noise. Dr. Junhee Kim at Oxford Ionics and Dr. Juha Nikkola at IQM have spent years pushing these numbers down. In 2024, Kim's team reached a record 99.99% fidelity for 2-qubit gates in trapped ions. Nikila's group at IQM hit 99.91%, with superconducting qubits, a technical triumph, but still just brushing the edge of what's needed. The critical threshold for reliable quantum error correction sits at about 0.01% error per gate. Only below this line does error correction become effective, allowing logical qubits to protect information long enough for meaningful computation. Above that threshold, errors multiply too quickly. Even the most advanced quantum processors can string together only a few hundred or thousand operations before the answer dissolves into randomness. The result is a stark reality. Without error correction, the dream of practical quantum computing remains out of reach. Progress now depends on crossing that threshold, not just for a handful of qubits, but across entire chips, every time, without fail. In December 2024, Google's Willow processor crossed a line that had haunted the field for decades. By wiring together 101 superconducting qubits into a distance 7 surface code, the team achieved something long thought out of reach: logical error rates that fell exponentially as the code grew, with suppression by a factor of 2.14, and logical lifetimes stretching 2.4 times longer than the best physical qubit. This wasn't a one-off. That same year, Dr. Krista Svor and the Microsoft Quantinuum team used just 30 trapped ion qubits to build 4 logical qubits, driving error rates 800 times lower than their raw hardware. The research community responded in force. Over 120 peer-reviewed quantum error correction papers appeared in 2024 alone, more than triple the output from just 4 years earlier. For Dr. Hartmut Nevin at Google, these results proved that engineering could finally outrun decoherence, at least for a handful of logical qubits. Engineering teams are now racing to stretch quantum memory further, drawing on a growing toolbox that spans physics, materials science, and computer science. Cryogenic cooling remains the foundation, driving temperatures down to 15 millikelvin to freeze out thermal noise. Layers of mu metal and superconducting shields block stray electromagnetic fields, while dynamical decoupling, rapid sequences of control pulses, can boost coherence by factors of 10 to 100. Material scientists are refining substrates, turning to isotopically pure silicon-28 and cleaner interfaces to cut down on 2-level system defects. Quasi-particle traps, crafted from normal metals, now siphon away damaging excitations before they can poison the qubits. Professor Matthias Treuer, a leader in quantum algorithms, points to new error-correcting codes that could slash overhead by 100 times, making millions of physical qubits for fault-tolerant computing a realistic target by 2030. The central question remains: can these solutions scale, or will the fundamental fragility of quantum information always set the pace? As quantum computing edges closer to reality, the fight against decoherence defines the pace of progress. Every microsecond gained is a battle won against nature's most fundamental limits. The next leap won't just be technical, it will reshape what's computationally possible. The countdown to true quantum power has already begun.